Okay, last time we talked about a couple of really interesting experiments that were done by a French physicist, Charles Dufay. And you saw some of those experiments with Mr. Van Dam the other day. And what you should have been convinced by was that electricity comes in two kinds, because you can charge up an object and then have another charged object approach it, and let's say the first object will repel it, approach it with another charged object, and that one will attract it. So if you can have two electrified objects that have opposite effects on the exact same one object, then the electricity has to come in two different kinds, right? Because one kind's attracting in this case, and the other kind's repelling. Now,
would you move that eraser on the board?
Oh, yeah.
Great, thank you.
And so that's, just so you're completely convinced of that, I want to show it to you again. So what we have here, let's see, let me turn it like, Tom, is it better if I turn it like Salem? Oh, you can stand up, or yes, stand in front of your desk, or is it?
That's good. Just
Okay. 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 So let's take this piece of plastic and rub it. And what should we see here? We should see it attract if it's not already electrified. There we go. It attracted and touched. Did you see that? And now it repels. Okay, so that's exactly what von Guericke first noticed, that after it touches, it repels. Now, let's take a different object, charge it up, and this one's repelling, right? That one's attracting. Drew.
But how come when it touches that, it doesn't repel like it does with plastic?
Oh, well, it didn't, because I think in this case what happened was it had already been charged up with, it had been electrified with the other one. See, let's do it again, starting with a neutral object. Okay, now charge up the white pipe here. Touches, attracts, and wait. Oh, you're right. Huh? What's going? Oh, now it's repelling. It didn't pick up enough the first time. Now it's definitely repelling because it's picked up enough from the pipe. Okay, and now if I take this other clear plastic object, it'll attract, right? Yep. Now it touches and repels. So you've got two objects attracting this one and repelling this one. Okay, that's exactly what Dufay noticed for the first time in 1734. And then went on to test a whole bunch of different objects to determine, which of the two kinds of electricity that they had when you rub them. Now that's an amazingly simple experiment, right? And he's discovered something absolutely fundamental and remarkable about the world, that electricity comes in two different kinds. Now make the contrast here between when we studied gravitation last year. Does mass, how many different kinds of mass are there? Try. One, right. All mass attracts all other mass, right? And that's what people expected to see when they started studying electricity. And all the first observations that they made supported that initial idea. That, I mean, remember they discovered electricity by first rubbing a piece of amber and seeing it attract little pieces of straw. And so they just thought of electricity as this weak attractive force. And it was an attractive force like gravitation was an attractive force. Well, Dufay is the first one that thinks of, first he notices, I mean, first, look what you have to do to make this discovery. He first charges up an object and holds it up to his gold foil, okay, and sees the attraction. Okay, now that's the exact same kind of effect that everybody had seen for centuries before him. But then he lets him touch, and he notices that then it repels. Okay, now only one guy before Dufay had really taken note of that, and that was von Guericke. But Dufay realizes that this is a general principle, that if you have an electrified object and you let it, it'll attract a non-electrified object, but then when they touch, it'll transfer some of its electricity to it, and then it repels it. So that leads him to the idea that all objects, all electrified objects, must repel each other. Okay, that's what he thought at first. And because as soon as you allow an electrified object to transfer some of its electricity to another object, they repel. But then that just sets it up for him making his next discovery when he thinks of electrifying the gold leaf and then charging up a different object and seeing how it reacts. And you just saw exactly what Dufay saw. So let's just review here. Dufay discovers there are two kinds of electricity. And this was in 1734. So this is just 5 years after Gray discovered electrical conduction. And Dufay's, let me see. Dufay quickly convinces himself by testing a whole bunch of different kinds of materials and classifying the materials into two categories that have either the glass type of electricity or the amber type of electricity. And he convinces himself with these experiments that bodies with the same kind of electricity repel whereas bodies with opposite kinds attract. Now this is still at a, I mean, one of the things I love about this experiment is, I mean, it's so simple, and yet he makes this major new discovery about the world, and we'll see as we go on in this course how well, I mean, you know how important electricity is, and this is absolutely crucial to our knowledge of electricity. And and this is an experiment you can do with a dollar's worth of material in your garage. So it's that's the nice thing about these when science is at this early stage. Today's experiments generally are not quite so simple. Drew?
Would you even be able to electrify the dollar? Like if you had a dollar, would you be able to do the same thing as you did with that?
Oh, yeah. I mean, all you need is you need a good insulator here, so the electricity doesn't get away from you. And that's one of the things that was happening when Mr. Van Dam originally demonstrated a couple of these experiments for you. The experiments that didn't originally work, I think one of the reasons they didn't work was because there was a thread, and some of the we were just fooling around actually and realized that the thread really was conducting electricity. So Gray was right about threads conducting electricity. So some of the electricity was getting away. Here we eliminated the thread and just used electrical tape. So you do have to be careful setting up the experiment in order to make sure that the electricity doesn't get away on you. But if you can do that, yeah, could you hang a dollar bill here? Yeah, it wouldn't work as well because it's first of all, it's heavier, so it won't move quite as easily as this little piece of foil.
So the ink wouldn't matter, it wouldn't do anything to it?
I mean, a dollar bill wouldn't be I mean, is that a conductor or an insulator, a dollar bill?
Well, it's paper, so...
Right. It's an insulator rather than a conductor. So that means electricity doesn't move through it the way it does a metal. But you can charge it by direct contact, so it still should work. It wouldn't work as well. Okay. So let's, at this point in the 1730s, people started getting really excited about these discoveries on electricity, and actually demonstrating electrical phenomenon became very, very popular. People would put on basically little electrical shows, and the public would come out to see these new principles being demonstrated. Now, in order to make the shows spectacular, you need a lot of electricity. I mean, the more you have, the more spectacular the demonstration can be. And so the people that were interested in demonstrating these electrical principles for the public started thinking about, how to generate more charge. Now they had, remember, they already had something better than, what we've got here, just rubbing a paper towel against a piece of plastic. They had von Guericke's machine, right? They could make a machine that would spin, say, a big ball of glass really fast, and while, say, you're rubbing wool against it or something. And so they would charge up, they could get more of a charge than I can get by rubbing this plastic tube. But it still wasn't a lot. Now, and one thing they noticed was that if you charged up, let's say you had one of von Guericke's machines and you spun it really fast against the wool, and you got it to charge up. Well, if you just walked away for an hour or two and came back, would it still be charged the same amount? Well, it turns out not. The electricity would, they found, would slowly leak off. I mean, you couldn't just charge it up and come back the next day and expect it to be still charged. I mean, the way they thought of that was that electricity was a little bit like a fluid, and it evaporated, you know, if you just left it out in the air. So one guy who was an amateur scientist, very interested in electricity, he had the idea of putting electricity in a jar that he could close, and so that it wouldn't evaporate. Now, this guy's name was E.G. von Kleist. And his idea was this. Let's say that he takes a jar and he's got his jar, say, filled up with water. And he puts he corks his jar, and then he sticks a wire through the cork and extending down into the jar and into the water. Now he takes his von Guericke machine, so he's got his ball that he's spinning around against his cat, and he charges it up, and then when he has a good charge on it, he touches his wire to it. Okay? So his idea is that he can get this electricity to run off into his bottle. Okay? And he can spin his glass ball around and charge it up really good, and then touch the wire to it. And then he can do it again, touch the wire to it. And then he can do it again, touch the wire. I mean, you can do this indefinitely, right? So he does that. I mean, not indefinitely, but he does it a few times. And he's holding this. Then he takes this jar. He's holding it in his hand here, and he touches the end of the wire here. Now, what do you think happens? Say.
He electrocutes himself?
Yeah, he gives himself such a powerful shock that his arm went numb, and that's how he discovered that you really can put electricity into a bottle. Say.
Did he sell that as an idea to one of those guys who used him as shows?
Well, yeah, I mean, these started to be used in these electrical shows all the time now. I mean, I'll tell you a little bit about that in a minute. Now, von Kleist actually, turns out he didn't even get to name his invention. I mean, he actually invented this first, but then a university professor invented it independently shortly after him, and this guy was a science professor at the University of Leiden in the Netherlands. And so this became known as the Leyden jar. So the professor ended up getting the name. I would tell you the professor's name, but I don't think I know how to pronounce it. It's very, very long. Let me see. Just for completeness here, the professor I just mentioned, his name Musschenbroek. Musschenbroek, yes.
What's with all the bonds and bands?
Oh, it's a common thing in the Netherlands. I don't know. So, anyway, we're going to stick with von Kleist here. And now von Kleist went about trying to figure out how to improve this invention of his. Well, the first thing I should emphasize, the first discovery that von Kleist made, that you don't hold the jar in one hand and touch this thing after you've charged it up. That's a bad idea. Yeah, Dan.
If you had like similar to that, but it was like 5 times as big,
Yeah.
and if you touch the wire, would it make a difference in like electrocuting?
Well, actually, they found that it wasn't so much the size. I mean, this original jar was plenty big, but he's going to find out how to make it even better than his original design.
That help burn it?
Nick.
Could he like take out the wire and we come back in a day or something to take the wire?
Oh yeah, that's the thing. See, he has solved this problem of people charging up this glass ball and then coming back the next day and finding out that it's not charged anymore. He can charge up this bottle of his, and as long as he sticks it on a wooden table, something, and so he doesn't. And he doesn't have this wire, connected to something on the outside that conducts electricity. The electricity just stays in there, and he can come back the next day, and it's still charged up. Yeah, Drew.
But doesn't like water not go good with electricity?
Well, I mean that's the whole point here. I mean, water does conduct electricity, and that's why him choosing water was a fortunate choice here. Now, he realized that, and he thought, well, one way I could make this even better, I mean, better in the sense of building up a stronger charge, is to use an even better conductor here. So what he thought of doing next was replacing the water with mercury. And he did that, and it worked. That improved it. Now, he would also find out that if you didn't use a really thick glass jar, but if the glass was a little thinner, that made it work even better too. And then eventually people, this wasn't von Kleist, but people after von Kleist figured out that if you coat the outside of the jar in a metal too, so you have the inside of the jar coated in a conductor and the outside of the jar coated in a conductor, then it worked really well. Drew.
I was listening to you, I forgot it.
Oh, okay. Well, listening to me isn't so bad. Troy.
If he just like dropped the jar and on accident and it broke, and would it just would there just be a lot of electrified water all over the ground and stuff, or
Oh,
what would happen?
yeah, I mean, whatever charge was in here would just be dissipated into the ground now. I mean, it's like I mean, if he put, you wouldn't even have to drop it. If you put this jar on the ground and then stuck this wire into the ground, okay, then you would find that there wouldn't be any more electricity in the jar. Yes.
So if you just wanted to keep it in a jar for a long time, would you cut the wire or take it out? Or?
Well, if that's right. I mean, after he's charged this thing up, he could just take the wire out and have the electricity stay in the jar. Yeah, say.
The ball he used was glass, right?
Hmm.
The ball he used was glass, right?
Yeah.
Would it work better if you used a metal ball instead of a glass ball?
Oh, no, then it wouldn't work at all. Turns out. The
What if you got
right. What you see, you need some kind of insulator to keep the electricity basically in the jar. If it's nothing but a conductor here, then, for instance, I mean, if you're holding this jar, and let's say it's a metal jar now. As soon as you touch the wire to this charged up glass ball, well, what do you think is going to happen? Yeah, I mean, you're holding this.
electrify his heart if it's really strong?
Well, no, but as soon as you touch the wire once to the electrified glass ball, the electricity is going to run through the wire, right? Now, if this whole jar is just nothing but conductor, it's a metal jar, it's going to run right through to your hand and then through you into the ground, right? So it's you're not going to be able to keep any electricity then.
If you kept putting electricity in water for like a long time, would it make a difference in like the way it would shock you?
Would it make a difference depending on how long the electricity has been in there?
Yeah.
Like,
I mean,
if von Kleist had, rather than touch this into the wire while holding the outside of the jar right away, if he'd come back the next day and done it, would it have felt any different? No.
like keep doing it for like a couple
And what if you
minutes.
put more electricity?
Yeah.
If you kept doing it,
Oh,
doing it.
yeah. Well, that's then you could he could get so much electricity in there that he would actually really do himself damage rather than just make his arm go numb. Yeah.
Oh,
Yeah.
is there a point where you can't put any more and like electricity in something?
Oh.
Or would it break that it had so much?
Yeah, that's a good question. Yes, there is a point at which this thing will break down. And it actually depends on, I mean, what that point is depends on how thick your glass is and the material of what people would discover later, for instance, is there were materials that worked even better than glass. Certain kinds of wax worked even better than glass. So you could put a bigger charge without having it break down. But eventually, yeah, it will break down. There are limits to how much electricity you can put in a jar like this. Sayla.
What if you used a metal cork or something? Or like a lid?
Like use
Metal-
what?
Metal cork or lid?
Oh, let me see. If the stopper here were metal, well, what you don't want is a connection between the inside and the outside of the jar. So as long as there isn't any connection.
Let's say
Yeah.
The cork was like just ordinary cork material. Then the bottom part was like metal. What would that?
Oh, it wouldn't do anything. The important part is to have metal on the inside up against the glass. And they found out you can make it better if you have metal on the outside up against the glass. Drew.
Two things. Would it matter if like there was no water, no nothing in there? You just put the wire in there and then charge it up. Would it like
Yeah.
not work?
No, that wouldn't work.
And then how did he test it? Did he just keep touching it, or did he use his cat?
Well, eventually he had the idea of using other people rather than just himself.
Take his wife to it.
Well, for instance, in these electrical shows, one thing they would do now is they would have one of these Leighton jars full of electricity. They would have a Von Guericke machine, okay, that they had been cranking up, and they would have an attractive woman, okay, who would be, say, sitting up on stage on a good insulator, okay, and they would just charge her up, okay, and then they would dare men in the audience to kiss her. They would get a big shock, and everybody thought that was very amusing. Now, of course, the girl would get a shock too, but presumably she was being paid for it and was.
Get that anyway when you kiss it.
Okay. So let me see. What else did I want to tell you about this? So let me just review here how they optimized this design. If you have the inside say coated, that isn't working very well, with metal, and outside coated with metal, now, while you're charging this up, and there's one thing I haven't mentioned yet. It is crucial when you touch this wire over and over again to this charged up ball. You don't want to have this jar just sitting on a wooden table and not touching it. That you need to hold it in a hand or put it on a metal container. So it's important for the outside to be connected to something that conducts electricity. Your hand or a metal stand or something like that. Once you've got the thing charged up, then you can set it on an insulator and then just keep the charge in the jar. Okay. Drew.
But why would that matter? Wouldn't it
Why would that matter? It's a good question.
Wouldn't it be draining into your hand or something? Or?
Somehow the outside of this jar, in order for the inside to hold the electricity, the outside has to have access to electricity too. It has to be connected to a conductor. Your hand, something metal.
So does it take a little bit of the electricity, or like over like 100 years, would like the electricity drain, or would it always be kept in no matter what?
Oh, if you just left it forever. Well, I mean, if you left it forever, it would eventually drain away. But forever is a long time in this case. It's not like the ball that you come back the next day and it's not charged anymore. And the reason, well, can you guess what the reason might be for some loss of electricity over time?
Could it just slow down or something?
I mean, well, is there anything that might connect, the inside and the outside of the jar? I mean, there's air, right? See, what if you put it in a vacuum? What if you put it in a perfect, you had a perfect vacuum pump, and after charging this thing up, you stuck it in the vacuum? Well, then it would probably stay charged pretty much forever. Drew?
Well, wouldn't like inside of the jar, the water would eventually evaporate, right? Or not?
Oh, if you were using water. Well, presumably you have it corked. I mean, they stopped using water after a while. They were using metals on the inside of the jar, because they found that worked better.
Oh, like you don't even have to have any liquid in there?
Oh, you don't have to have any water at all. You can, yeah, the water is not, was the first thing that von Kleist tried, but it's not essential. All you need is some kind of conductor in the jar and up against the glass. And there are better conductors than water. I mean, so they found that metal worked much better. Ben?
What if the experiment, like, the items in the experiment were so big that you could fit in the bottle, like swimming around in the bottle?
Oh, yeah.
Would you get electrocuted after a while? 'Cause, like,
Oh. Okay, let's take that one. Let's say that we do this on a huge scale. Okay? We've got basically a glass swimming pool here. Okay? And we have the inside of our swimming pool is, let's say, made of metal. Okay? And we've been charging up, a huge glass ball on the side of the pool, and taking a wire from sticking it in the water and touching it to this huge glass ball, and we keep doing that like 1,000,000 times. And our swimming pool is coated in metal, but then there's an insulating substance, say glass, and then metal on the other side, okay, that's hooked up to the ground somewhere. Okay, so this is a huge Leighton jar. And now we just jump in and start swimming around. What happens to us? Do you?
No, you don't get it.
Yeah, Nick's right. No problem at all swimming around in that pool.
because you're an insulator.
Wait,
Yeah, Drew.
but electricity, it does electrocute you. If like electricity did hit water, it would electrocute you through the water. How come that's not electrocuted? How come it wouldn't?
Well, I'm the first guy to explain how this Leighton jar works is Benjamin Franklin, and we haven't gotten there yet. But after I explain to you how the jar works, then you'll see why this example of the huge jar with the water that we can jump in and swim around in wouldn't electrocute you. Evan? Troy?
Well, if you made it a vacuum and you gave everyone breathing devices, would it still not electrocute you?
If
If you put the pool in a vacuum and you gave everybody like little breathing things?
no,
Uh,
you can. I'm not sure I got exactly what you're what you're imagining here, but it sounded wrong to me. So.
It's the way you get electrocuted if it's a big swimming pool, you have to touch the side of the roof
Well-
and then the water at the same time.
Yeah, I mean, notice, okay, I've only given you one instance of how von Kleist actually got a big shock, right? How did he do that? How did he get the shock? He was touching the outside, right? He's holding the bottle in one hand, and he used the other hand to touch the end of the wire. So somehow, now remember, I've told you that the way this thing, they found it works best is to have metal coating the inside of the glass and the outside. Well, what's happening when von Kleist is holding the outside and then touching this wire that's connected to the inside?
He's going straight to him.
Obviously, I mean, electricity is somehow running, say, from the inside to the outside through him. Okay, so that's the way you get a shock. If you connect the inside of the jar to the outside of the jar, and it's connected through you, then that's the way you get the shock. Now, in the pool example, we were just inside, right? No part of us was connected to anything outside, so there's no way the electricity can run through us. No.
Is that why birds don't get electrocuted when they sit on the electricity wires?
Well, I mean, there's several reasons for that, but yeah, I mean, you have to be basically, I don't know what we could call. You have to be in the path of the flowing electricity, and the path has to be through you. You know, if you're just standing on top of a conductor, say that has a bunch of electricity going through it, you're not going to get any electricity through you. The electricity would rather run through the conductor. Yeah.
What about the birds that sit on the little telephone wires?
They're safe.
Are there little claws?
Well, is there? I missed that last comment. What was that?
Are there little claws, rubber or something?
They have rubber claws. No, most of them don't. No, but there's no path of the electricity. I mean, if you were to break the wire, okay, tie one side of the wire to the bird's foot, tie the other side around his neck, okay, then you'd have a bird that was in trouble, because then the electricity would have to go through him. Okay, but if he's just sitting on the wire, electricity can flow. It doesn't have to flow through him. It won't flow through him. Drew.
What if there's two wires and they're right there, and you touch them at the exact same time when they flow through you and electrocute you, or they just go through you and go to the other side?
Yeah, I mean, if you have if you have this kind of a case where you have put a bunch of electricity into this jar and then you give it the opportunity to flow out through you into another conductor.
Like another jar.
Right. Like in this case,
You have two of those
in this
jars.
case, he's got his hand. I mean, we've already proven earlier. I mentioned that Gray was the first person to do experiments, on boys, right? And he showed that people conduct electricity. Okay, and so you're a conductor. If you're grabbing this jar, and the electricity can flow through you to the ground, it will. Okay, let me. I'm out of time, so let me quit. We'll pick it up next time.